Hello, welcome to another Cosmology Talk. Today we have Steffen Hagstotz, who is a postdoc at the Oscar Klein Center at Stockholm University. In today's video, he talks about fast radio bursts and primarily how they can be used to measure the Hubble parameter, or the expansion rate. He also goes a little bit into how they'll be useful as a measure of the density perturbations in the universe, but it's mainly about the expansion rate. The way they use the fast radio bursts to measure the expansion rate essentially is through a dispersion measure to tell how far away a given fast radio burst is. The light from the FRB gets dispersed, in other words, different frequencies travel at different speeds as it travels through the intergalactic medium, and therefore the dispersion grows larger and larger over larger distances. So you can tell how far away it is by how much it has been dispersed. Because this is about the Hubble parameter, it's very interesting for obvious reasons. It gives another measure of how fast the universe is expanding and can maybe help shed light on this tension that is fascinating all of cosmology. So I hope you enjoy the talk. Thanks for coming today, Steffen. Do you want to give us a brief summary of what you did in the paper?
Sure. Okay. So the good thing about the paper is that basically it's all in the title. So it says that it's a measurement of the Hubble constant using fast radio bursts, and that's exactly what happens there.
Cool. If someone's remembering this talk and the paper 6 months from now, and there's only two things they remember, what would you want those two things to be?
The main takeaways, I think, will be that fast radio bursts are really cool and interesting, and it's the right time to get excited about them. And they're actually useful. So we can already do interesting science with them. For example, this Hubble constant measurement is one example of what we can do now. We're not competitive yet, as we will see, but I think this will change pretty soon. So now is the right time to start thinking about new projects, basically.
You do say in the paper that at some point, percent level accuracy is not out of the question, which would be competitive. I guess that probably going to come up in the talk, and if not, I'll ask a question. But I guess one worries that systematics might be problematic, but who knows? I mean, the whole Hubble tension might just be systematics in the first place. So who knows? Why did you do this? For example, what questions were unsolved that you wanted to solve? Why were they unsolved? Why did you want to solve them? And basically, why did this paper come into existence in 2021 and not 2018?
So with fast radio bursts is actually very interesting because the data is so new. So what we did in the paper, I think it could have been done maybe late last year, but not before that. So basically, the data that we're using is very new. And as I said, there's more coming. So this field will keep changing. And so we wrote a couple of papers on fast radio bursts. The others were forecasts. I will briefly mention them in the talk, but the main focus will be on this latest paper. And this whole thing started quite recently, actually. So as you know, we started thinking about fast radio bursts at the first Cosmology from Home conference.
Yeah, or the little practice conference that we ran. And Amanda Veltman gave a talk there, and I guess so she also gave a talk at Cosmology Talks about fast radio bursts. So if people want the background, they should check either of those videos out.
Yeah, Amanda's talk is great. So it's highly recommended if you want to learn more about fast radio bursts. So that's basically all I knew when I got started in the field. I just had Amanda's talk and went from there.
Yeah, and I guess for the specific paper that we'd be talking about today, there's all of the Hubble tension interest that I guess the super interesting thing about this is that it's independent from Cepheids or supernovae, or I mean, there are other similar things like the strong lensing result, which has also been covered here by Simon Berra.
So I think those are the very nice prospects of using fast radio bursts for these measurements, because it's important to get more independent opinions on the whole Hubble tension.
Do you want to get into the details of the paper?
This is the archive number of the latest paper, and I mentioned these two other papers on fast radio bursts that we wrote. They are in the smaller numbers here. So again, I will briefly mention them, but I will mostly talk about what we can do with fast radio bursts. I will not expect everyone to have seen Amanda's talk before the video, so I will have a very short introduction. Okay, and all of this is work that I did together with Robert Reischke and Robert Lilo. Okay, maybe let's very briefly talk about fast radio bursts and what they are, because I think lots of people still haven't really heard of them, especially cosmologists. So
when you say what they are, I mean, I guess you mean what they are in an observational sense, because the vibe I got from Amanda's talk is that we're not 100% sure what's causing them. But
exactly, yeah. So the interesting thing is that we don't really know what they are. So they are radio signals for us right now. And the first one was discovered in 2007, which is still quite recent. So it was just in archival data. So this was a discovery that was missed the first time, just because people didn't know what to look for, essentially. And these pulses are very short, so in the millisecond range, and they're very bright. So it's very difficult actually to know exactly how energetic they are because we don't know that much about the mechanism, but they're definitely bright enough to be seen over extragalactic distances. So I will talk a little bit about that. So they have a variable frequency range. They range from 300 megahertz up to gigahertz. The pulses look different. I already mentioned that they're coming from outside the galaxy, and I will briefly talk about how we know that. So now we know about a bit more than 100 events, but we're very hopeful that actually soon we'll have thousands and thousands of them, because now is exactly the time when these dedicated searches actually start.
What sort of telescopes do the dedicated search? I mean, radio telescopes, I guess, if they're radio bursts, but...
It's very exciting actually for radio astronomy right now. So there are a couple of experiments, CHIME, HIREX, for example, ASCAP. So Amanda mentioned a couple of them and went into details. I don't want to repeat all of that. So basically a lot of experiments right now are preparing eventually for SKA, for the big radio astronomy era. And all of these new radio telescopes now have dedicated FRB searches. And as we will see, the most important component is that you actually look for something that's only milliseconds long. So you just have to do the data analysis in a bit different ways. And the other thing that's very valuable for FRB searches is to have sufficient angular resolution. So that was a problem with the first ones that we discovered. The angular resolution was very bad, and we couldn't figure out where they're actually coming from. So some of these bursts are actually repeating, and they're different patterns. So some are quite regular, some are very irregular, but the whole period is repeating regularly of like these irregular bursts. And some are not repeating, or we haven't seen them. It's hard to tell at the moment. So it could just be that we are actually looking at very different events.
So when you say that they might be repeating, but we haven't yet observed it, you mean not that that's not necessarily a data analysis problem. It could literally just be that the repetition hasn't physically happened yet?
Right. So the repeating ones we know, they repeat in a week time scale regularly, or like a couple of 100 days irregularly. So those are pointing towards something like orbital timescales when you think about it, but that's all we know. So it could be that they repeat on longer timescales, also the others, or we missed them somehow. So the interesting thing about FRBs is then, of course, that we really don't know what's causing them. So this is still a mystery. Okay, so there's a very nice overview if you're interested over like the mechanisms that people discuss. This is this living theory catalog. There's the link there. And they do a very nice job of basically listing all the possible explanations and going through the different consequences that these theories would have. Yeah, so how you can check all of these theories with observations. So we have some idea because recently there was this paper by the CHIME collaboration. So they saw something from a galactic magnetar that looked like an FRB. So this was a magnetar within the Milky Way. Was not as bright as the other FRBs that we see. So it could be that they are somehow connected with strong magnetic fields and magnetars.
I mean, I remember Amanda's talk, which was before the 4th of November 2020. She listed magnetars as a leading candidate. So it feels like this is prediction being verified rather than observation leading prediction. So
it makes sense, right? Like the first thing you think about is something like pulsars, I guess.
I'm not sure I know enough about astrophysics to have a first thing I'd think about, but okay, I'll believe you that if one knows what they're talking about, they'd first think of pulsars.
Well, magnetic fields are always like, if you want to explain something.
Yeah, I guess if you want to create an electromagnetic thing with a large wavelength, magnetic fields seem plausible. Yep.
All right, and this is an overview. So this is the Milky Way, and all the dots are the events that we know so far. And you can see immediately that they are basically distributed all over the sky. And there's a little bit of a bias there because that's also the parts that we cover with radio telescopes. So different telescopes cover different parts of the sky, of course, but they're not really correlated with the Milky Way. Yeah, so the size of the dot is shown here as the total dispersion of the pulse. And this is
the skeptic inside me who wants to, rule out all possible explanations. In some sense, maybe it could be caused by dark matter in a halo. So you'd have to come up with some reason why dark matter is producing a radio signal, which, okay, is not a super straightforward thing. But in principle, it could be from the galaxy if it's doing that. I guess there's other reasons why it's not likely to be in the galaxy as well, though.
Exactly. So this is part of the explanation, but yeah, you're exactly right. The other reason why we think that they're extragalactic is the dispersion measure of the pulse. Yeah, so this has to do with the radio pulse basically traveling through the intergalactic plasma, and the different pulse frequencies are delayed. So this is a very typical dispersion proportional to 1 over the frequency squared. And so I show here an example. This is actually not an FRB. They don't look that nice. This is a pulsar, but it demonstrates the principle. So you have all of these different frequency bands, and the arrival of these frequencies is more and more delayed. And this pulsar has a very small dispersion measure.
When you say it's more and more delayed, should I be able to see that by eye or?
Yeah, okay, it's not, okay, as again, for FRBs, it's even more messy. This is the nicest example that I found. But yes, so basically the idea is that if you measure the peak of the pulse, it's more and more shifted.
But when you do good statistics, you see that. But I shouldn't be able to see that by eye, or okay.
Exactly, yeah. Okay, and the idea is that this total delay of the pulse is proportional to what people call the dispersion measure. That's dm. So dm in this talk will not stand for dark matter. It's a little bit confusing. And the dispersion measure is basically just the integrated electron density along the line of sight.
So it would be some piece of the constant of proportionality in the pulse delay equation, or?
Exactly, yeah.
And it's not then frequency dependent.
Yeah, so you fit basically for this frequency dependence, and the amplitude is then the dispersion measure. So you can determine it from the data actually very, very well. So the measurement error on the dispersion measure from the pulses is like ridiculously small for all practical purposes. Okay, and yeah, and now we come to the second reason why we think that these pulses come from outside the galaxy, because these dispersion measures are very, very large that we observe. So that means that they have to travel through a lot of electrons, basically. And it's really mostly electrons. So everything that's ionized basically delays the pulse, but in practice, it turns out that electrons are just overwhelmingly relevant for this effect.
There's no degeneracy here with the actual initial shape of the pulse that was sent? How is that degeneracy dealt with?
Yeah, so the only assumption you have to make is that all the frequencies of the pulse are emitted at the same time. But actually, you would start seeing this in the data if it wouldn't be true. So you can actually check for this. Because, well, we will see that later, but we have a couple of fast radio bursts where we actually know the distance, and then we can check these assumptions. No, but you're right. For now, what we're assuming is that they're all emitted at the same time. All right, and if we look at the total dispersion measure from these events, then so we have 3 contributions essentially. So we are somewhere in the Milky Way here, and we're looking at an FRB. This is not to scale, further away. And we observe an FRB in some other galaxy. And then the total dispersion measure is basically caused by the electrons in the Milky Way, and by the electrons in the host galaxy, and by everything in between. So basically, if we want to use this, then we have to build models for all the components. So luckily for the Milky Way, we have a quite good understanding of the electron distributions. And that's partly because we can observe the gas distribution in the Milky Way. And the other thing is that we have a lot of pulsars in the Milky Way, and they're also giving off radio signals. So they are also dispersed by the electrons. So we can actually use observations of Milky Way pulsars to check these models.
I guess I'm maybe getting ahead of you here with the question I'm about to ask, because you haven't yet kind of actually told us how this dispersion measure is going to lead to the Hubble parameter, the expansion rate. But I guess inside the Milky Way, my initial naive thought was that it kind of doesn't matter because every FRB has to come through the Milky Way, but maybe there's like a directional dependence. Is that the problem, that something that came from the north might have had more dispersion than something that came from the south or the east or the west or whatever? Is that the problem, or?
Yeah, absolutely. Like in the extreme case, something that's coming through the disk has a way higher dispersion than something that's there. Yeah, so I will come to this in a second. But yeah, I mean, spoiler, the idea in the end will be to use the dispersion measure as some kind of a distance proxy. That's why we want to understand all of these components that contribute. Okay, so we understand the Milky Way pretty well. We understand the host galaxy not well at all. This is the largest problem right now. So basically, we have to make some statistical assumptions about the host galaxy, but apart from that, it's very difficult. And then there's a large-scale structural component, which I will come to in a second, that we can actually calculate. This is where most of the interesting information will end up. So you want to disentangle these effects, if you can, observationally. And it turns out, okay, so the Milky Way component will just depend on the direction on the sky, but not on redshift. So we'll come to the large-scale structure component in a second, but yeah, it will have some redshift scaling. And the host galaxy contribution just scales with 1 over the 1 plus the host redshift. And the reason is that any dispersion that you imprint in the beginning then gets redshifted on the way.
So yeah, so you assume that the initial dispersion is not time dependent, that a galaxy at a redshift of 2 is the same as a galaxy at a redshift of 1 and at 0.5 and at 0.3.
Yeah, so they are, yeah, exactly. Yeah.
Is that valid? Like if the star formation rate is different, do you have different amounts of electrons? And
yes, so if you talk about redshifts 1 or 2, galaxies will absolutely be different. Luckily or sadly, depending on how you look at it, we don't have any FRBs at that high redshifts yet. So most of them are at quite low redshifts. Okay, but the idea is that basically these components can be distinguished statistically, at least. And right now we're not quite there yet, but I will come back to this. Okay, so maybe let's have a look at this large-scale structure component again, because this is where really most of the information that we want is. Okay, so there's the electron density in there. As I said, basically we just integrate along the line of sight over all the electrons, and that will depend on how many electrons are ionized and basically how many electrons there are. Okay, so the baryon density. And if you expand that, then you become sensitive to perturbations in the electron density multiplied with some bias factor. So in theory, you could use this to probe the density field.
And this is what you've kind of looked at in other papers, right?
Exactly. So this is what the past papers are about. Forecast papers, basically, how you could use this. You can look at the ionization history. So this is mostly interesting if you actually manage to measure them at high redshifts, because at low redshifts, everything is ionized, basically. It's a bit boring. You can use the whole thing as a distance measure. So this is what most of this talk will be about. Or you can try to measure the baryon fraction. So this is what I think Amanda talked about quite a lot.
Yeah, I think she gave her talk very soon after FRBs had kind of been in the news for the missing baryons or something silly like that. The missing baryons got found for the 20th time and made it into the news for the 20th time.
Exactly. So there was this paper in Nature that basically found the missing baryons using FRBs. Exactly. So you can basically pick your quantities that you want to constrain with FRBs, but there's a lot of information in there. And so I will very briefly mention the density field. So what you can learn about the density field. This is these 2 last papers, and then I will really talk about the distance measure. Okay, so this will be a very brief excursion here. So if you want to measure a large number of FRBs, you don't really have to assume that you know redshifts of all of them, but you can basically just use angular clustering, right? So the first thing you would do is something like you write down a 2-point function, because we're cosmologists, that's what we do. But it turns out if you do that, like if you just correlate the FRB densities on the sky, then basically you have a bad galaxy survey, because FRBs live in galaxies, but you have far more galaxies than FRBs. Okay, so what you can do instead is like you can correlate the dispersion measure of the FRBs. And as I showed before, that basically if you expand it, you become sensitive to the density perturbations. And this looks very much like weak lensing. Okay, so it's some integrated measure of the power spectrum in the end. And FRBs are a little bit special because it turns out that for large distances, this cosmological contribution is much higher than what we expect from the host galaxy. And for weak lensing, the opposite is true. If you think about what the weak lensing imprint on the ellipticity of any single galaxy is, it's very small. And here we are in the opposite regime, where like the dispersion measure of a single FRB is dominated by the signal component. So yeah, it's really something like super weak lensing, but it's still very sparse. So we don't with weak lensing, we can basically go down to very small scales because there are just so many galaxies.
and every galaxy gets lensed, I guess, whereas not every galaxy emits an FRB.
Exactly. Yeah. Okay, so if you do these dispersion measure correlations, then you can probe the density field on very large scales. Then you can think about what to do with that. So on small scales, you're not competitive with other methods, but you can reach very large volumes. And there are a couple of papers here. So these are the first guys that really looked at these dispersion measure correlations. You can look at cross correlations with galaxy surveys. And what we thought about is that if you are constrained to very, very large scales, you can start looking at things like non-Gaussianity, because this is where you would see it. And potentially you can cover very large volumes with FRB surveys faster than with galaxy surveys. So this is something we will have to see, but yeah, this would be the appeal. And the other thing is that you can look at anything else that imprints correlations on your time delays. So in the second paper, we looked at what if the time delay caused by the gravitational field between us and the FRB is something non-standard. And that's also something that would end up showing up on very large scales. And then you can see it with the FRB correlations.
You said that FRBs can get to the very large scales potentially quicker than weak lensing. Is that because the benefit of the weak lensing is that just you see lots and lots and lots of more galaxies than you do FRBs, but the benefit of FRBs is that an individual FRB has a stronger signal than a galaxy, and therefore from large distances perhaps you might see more FRBs, well, a bigger fraction of FRBs to galaxies because they're so bright. And so before you actually capture all of the galaxies, FRBs might temporarily be like the better thing. And then if you did manage to see all the galaxies would still, the weak lensing would still win. Is that, have I got the right picture there? Or
that's right, yeah. So the other advantage of FRBs is kind of that radio telescopes are covering a large fraction of the sky right now. So we have a lot of them in the northern and in the southern sky. And for these dispersion measure studies, you could combine them. And then you cover like a large fraction of the sky up to redshifts of potentially 2 or something. And that's just a very, very large volume. Eventually, with galaxy surveys, you could cover the same volume. It just takes a bit longer. Okay, so back to the main topic, essentially the distance scale.
I see the H0 has appeared in the equations.
The H0 has appeared in the equation, exactly. So this is just a rewritten expression from before. And what I did is basically I wrote out the integral over the line of sight into an integral over redshift. And this is where H0 appears. And now you can see that there are all of these prefactors that basically come from the electron density. This is the ionization rate. This is the fraction of electrons in the intergalactic medium. This is something, yeah, I will talk about in a second. And then we are stuck with an integral basically over the dimensionless Friedmann equation. Okay, and then, so this is the main component of the dispersion measure, the large scale structure component. And this is mostly what we will use as a distance proxy in the end. And you can see that this pretty much looks like a distance. It has different prefactors. So one problem is that we are like everything that leaves this prefactor unchanged, you can't distinguish, right? So in the end, we want to measure H0, but then, for example, we can only really constrain the combination of the baryon density and H0.
I guess you've also got this chi and f.
Luckily, I think, so again, the ionization rate at low redshifts is very well understood. Basically, everything's ionized. So this is not a huge problem. But this IFGM is FIGM is a little bit of a problem because this is essentially the fraction of electrons that's free. So to calculate that, you have to make some assumptions over the star formation rate, essentially, like the fraction of electrons that's actually bound in some object.
And I see that's also not written as redshift dependent here.
Exactly. So in our case, again, because most of the FRBs are at low redshift, this is essentially not changing. But for once you become sensitive to higher redshifts, absolutely you should put this in the integral. So this is a bit simplified. Exactly. And then you can essentially pick what you want to measure with FRBs. So this Nature paper that I showed before chose to measure omega baryon, essentially. And they made assumptions about the other parameters. So they took like an external H0 measurement. But I'm a cosmologist. I don't know. I find more interesting is like I think we have a pretty good understanding of what omega baryons is from the early universe observations, and then you can use this to measure H0. But it's important to point out here that FRBs alone can only determine this overall factors. So currently, what we did in the paper is either to assume CMB or BBN priors to constrain the baryon density. Exactly. So this is not entirely an independent measurement yet. So if you're interested, for example, in these like late versus early universe splits, like what does the late universe tell us about H0, or what does the early universe tell us about H0? This is not the clean split.
Yeah, I guess are there? What's the best late universe measurement of omega B? Like, just trying to think off the top of my head. Is it like galaxy cluster masses, X-ray temperatures? I don't know. What is it? Is it?
Yeah, so I think the best ones come from the gas fraction in galaxy clusters. So there are these F-gas measurements where you measure the baryon fraction in galaxy clusters, and then you have to measure omega matter somehow.
Which you get from weak lensing power spectrum measurements or something. Okay, so you could do a full late universe one if you were again trying to like make sure that any tensions are well, not make sure, but try and like be a detective and work out where any tensions are or aren't coming from. I guess at the moment FRBs are consistent with everything, but if and when they pick a side.
Yeah, exactly. So yeah, in the paper we mentioned this. So we don't do it for now because, as I said, like the statistical error is quite large. But eventually you probably want to construct like a late time only or early time only, or well, early time prior FRB H0 measurement. And then you can do exactly as you said, right? Like you can determine this from some late time probe. Okay, so let's come to the data. Okay, so what we do is essentially we just compile a dispersion measure redshift diagram with the FRBs we know. And right now we know 9 of them with redshifts. Okay, so there are 9 data points here. These are all FRBs where we identified the host galaxy somehow. And you can see that the highest redshift that we can get is like still below 0.7. Yeah, and this is basically why I was a bit sloppy before and I didn't write all of the quantities in the Z integral. So this is how our data looks like, all of these dots. The black line is our best fit result. Okay, so basically it's just this relation here. And the error bars that I show here mostly come from the uncertainty in the dispersion measure from the host galaxy. Okay, and then there's a bit going into details, but there's some events where we are not entirely sure whether the host galaxy is correctly identified. Like there's some ambiguity there. So we make this optional distinction between like a gold sample where we only include events that have a very good host identification, or all the other events. And you can see that also the other events kind of, they fit. Okay, so they're not too far off.
Is the frequency of the FRB itself sufficiently unpredictable that you can't even get a super crude redshift measurement of it based on just the frequency of detection, or is that wishful thinking? Or
yeah, so I don't know. I think if it would be at redshift 10, then you could do something. But because the frequency range is so large, like, yeah, we don't really know. Maybe once we have more of them, we can also distinguish different populations and typical frequency ranges that those populations have. So those are all the events that we have so far. The good thing is that there are reasons to be optimistic that this will actually become much, much better. So yeah, on the y-axis here, I showed the dispersion measure. And so the highest dispersion measure that we have now is like something like 600 in these units. And we know FRBs that have dispersion measures that are in the thousands. So if you very naively just invert this relation here, then you would end up with redshifts between 1 and 2. So much higher than what we have so far. So that suggests at least that we can see them that far out. We just have to find the host. Okay, and then that's basically the whole idea, right? Like, so you have this diagram. You have to assume some uncertainty concerning the host dispersion measure contribution. And so far we're quite generous there because we don't know that much about the host galaxies. And then you can get your H0 constraints. So what I'm showing here are like these little lines here are all the individual constraints. So you get one from each FRB event, really. And the joint constraint is then shown here for either the complete sample or the SCOLD sample, where we excluded some of them. And the constraint is basically the same. And the reason is that most of the ones that we exclude are at very low redshifts, where it doesn't matter much. Like the low redshift FRBs are dominated by their host galaxy dispersion measure. So they don't have that much cosmological information anyway.
For combining the errors here, have you assumed the errors are independent, or is there like some possibility that like there's modeling errors that are actually pushing everything systematically up or down or something? Or?
Right. So this is really just the product of all of the individual events. And yeah, I mean, it makes sense that the errors should be uncorrelated because, well, the different galaxies for sure have nothing to do with each other.
Sure. But the modeling, we could be systematically underestimating or overestimating the.
Yeah, so that's always possible, right? Like you can make your model can be wrong essentially. Yeah.
Your uncertainty is supposed to be capturing the probability that the model might be wrong to some extent, isn't it? Or...
Right. So what we include in the uncertainty is basically scatter for each of the components. So we know the uncertainty of the Milky Way model quite well. We roughly know the uncertainty of this line of sight component, like the cosmological component, because we can essentially trace along lines of sight in hydrodynamic simulations. That might not be perfect because those simulations might not capture all the physics that we care about, but they give us some idea. And the scatter that we find in this cosmological component is also rather small.
Mm-hmm. I mean, that also feels more trustworthy as a prediction and model and things. I guess I'm just, again, kind of wondering about a day when this black contour is like comparable in size to the green or blue ones. And how is one sure that one isn't just like, I mean, you could have a trustworthy uncertainty for an individual event, but if it's a systematic error, then that width might be there in all of them and in the same direction because, you know, you're assuming you've got too many or too few. Is the modeling something where the dominant error is a statistical one or a systematic one, I guess is what I'm at.
So that's actually something we look at next. So the question is, how many assumptions do you actually have to make about the host galaxy? And it turns out that you can relax those assumptions quite a bit. Like not yet, because we have very few events. But I will show in a second actually that this can become much better. Okay, so as you said, right, like what we want eventually is the FRBs to tell us, if possible, which ones of these lines we should trust. Okay, so it's very interesting to ask the question, how many FRBs do you actually need to do this? And you can basically, you can extrapolate the error. So what we show here is the percent error on H0 with the number of FRBs. And with a few hundred, you can get in the 1% range. And then the question is, of course, if you have a few hundred FRBs, you can do also a much more sophisticated analysis. Okay, so this is I'm showing the slide again, where we looked at the different redshift scalings. And this is really the key here. So we can distinguish the different effects because they have different redshift scalings. So we can determine H0 and the contribution from these host galaxies at the same time, really, if we have enough events. You can also, so this is something other papers talk about, you can also use the E of Z that's entering here to measure basically everything you want to measure about like usual expansion history stuff, like for dark energy constraints or curvature. But what we are looking at is now, can you distinguish these two contributions with a few hundred FRBs? And so what we did is like we generated 500 events. And with those, you can absolutely do it. Like you can, so this time we freely fit for the mean host contribution. So this is a mock catalog, so we generated them accordingly, but then you can absolutely fit for all of these quantities at the same time and still get a competitive H0 constraint. And for this analysis, I think we were quite conservative because we assumed basically that, if I just go back to our little diagram, we assumed that most FRBs would be in this redshift range. And as I said, the larger the redshift, the more powerful it is, because it's more dominated by the cosmological component of the dispersion measurement.
Yeah, that and the lever arm is more powerful.
Exactly. Yeah. So basically, this host halo contribution just decays if you go to very high redshifts. Yeah. So yeah, we were quite conservative and basically just assumed that this redshift range is typical. But as I said before, we have dispersion measures that go up to the thousands, so that are way higher redshifts. But yeah, we haven't seen the galaxy counterpart there yet. But with these new FRB searches, I think we can absolutely do that.
Okay, so there's no reason why an optical telescope won't see them, like that they're not bright enough or something.
We see galaxies reliably up to redshifts of 1 and beyond that. We can absolutely find these counterparts. It's a bit more challenging because you need higher angular resolution also. Right? But I mean, the angular resolution of these radio telescopes is really amazing. So for a lot of the events that we see here, like we can see that the FRB comes, for example, from the edge of the galaxy. Like you can actually resolve this. This is quite impressive. And so yeah, for the forecast, we wanted to be a bit on the conservative side. But the main takeaway here is that you can distinguish all of these components statistically, and you can fit for all of them at the same time. And you can still get a very good H0 constraint.
Just remind me where omega matter is coming into the theory.
Right. So basically, this is
Yeah.
So what we did for our analysis is basically that we chose CMB priors on the baryon density and on the matter density.
I have a question about timeline, but like you say 500 events, when will we get to 500 events? But I feel like I might be stealing your thunder. Maybe you're about to get to that.
Yeah, that's a good question. I'm not sure. So, okay, so I'm not in any of these collaborations, but my guess is that they internally have already a lot more events than they're telling us about. A lot of these events with host identification are really quite recent. So they were just published last year. Okay, so I'm not sure when we will have 500 events, but I think that's absolutely something that we can get in a year or 2.
Oh, wow. Okay, it's cool.
Or let's say 2 or 3, maybe.
Yeah, but less than 5.
We have to ask the radio astronomers and the observers. But yeah, these new surveys are really like very, very impressive. And from all we know, FRBs actually seem to be quite common. So we never looked for them. But as soon as we started really looking for them, then we found more and more. Yeah, so this doesn't seem to be a very rare phenomenon, far more common than like supernova explosions, for example. So I think the 500 is very doable very soon. And I mean, you can always, like for forecasts, you can assume what you want.
Yeah. With 100,000 events, the precision will be exquisite.
Exactly, yeah.
And yeah, it's kind of nice that I guess I was trying to think about the metaphor to the supernovae here, where they're standardizable candles rather than standardized. Like if we actually could know the intrinsic luminosity of a supernova, then we'd have super precise stuff very quickly with them. I guess the difference here comes down to that assumption that the frequencies are all emitted at exactly the same time, makes this a kind of standardized. I don't know what the right term then would be.
Yeah, I think it's a very good analogy actually with
Because if the frequencies were all sort of scattered around, then you'd have to do that distance ladder thing. You'd have to look at FRBs that were local and calibrate them, but you don't have to do that step. Well, I mean, you did say that you sort of do that step. I mean, maybe not in this paper, but that you look at local FRBs and you do see that they're all emitted at the same time. So it makes it maybe a safe prior that you don't see them scattered. And if you did see them scattered, then you'd have to do a distance ladder. So I guess this is...
So basically, if they're not emitted at the same time, this would show up as an effective host dispersion, right? So because that's what the host dispersion does. Like it delays the pulse before it...
Yeah, once they're outside of the galaxy, they aren't emitted at the same time because of this. Yes, that makes sense.
That's why I said like you can actually check these things, because you can... Then this would not be the host contribution only. This would be like some combination of intrinsic plus the host galaxy.
And it would still scatter, trend with redshift in exactly the same way, because it's just, as you said, the redshifting of that initial.
So this would not be a problem. I think there are some exciting things that you can also do with larger samples. So I think you can do much better than what we did in the paper soon, because you can also imagine that the galaxy types are different. You can imagine that like an FRB that's on the edge of the galaxy has a lower intrinsic dispersion measure than one that's somewhere in the center. And they also have less scatter.
I imagine there'll be hundreds of papers analyzing all of these effects coming soon.
Exactly. And once you take this into account, you can really basically determine the scatter that you expect more accurately. And then, also your limits become better. Yeah, so we don't know what FRBs are, but I hope that I convinced everyone that they're very exciting. So now is a very good time to start thinking about things to do, because the data is really what's limiting us right now, and there's a lot more data coming. And so we have this measurement of the Hubble constant. Independent is with a star, right? Like we absolutely put a CMB prior in there right now. But you can make an independent measurement using fast radio bursts.
But it's a completely different CMB prior to the one that, for example, the BAO people use, because for them it's the sound horizon that they have to take from nuclear synthesis or...
Right, but the sound horizon in the end is determined by the baryon density, right? Within the standard picture, it's equivalent. So once you fix the baryon densities, you fix the sound horizon essentially. So we also, like if you use a prior on the baryon density from BBN, then there are also assumptions that you have to make about expansion history in the early universe. For example, that N effective is 3.
But I mean, that'll be a super interesting thing to see in a few years, whether you match BAO's measurement of H0 taking that same prior.
Right. Yeah. No, and I think like this late time only measurement with FRBs that we talked about, that will be very interesting to actually do. Yeah.
Cool. Before we get on to what comes next, can you go back to the slide where you had the individual FRB measurements? With the strong lensing results, if one wants to see patterns in the noise, you can see maybe that there's a little bit of redshift dependence in their results, that as you go from low redshift to high redshift, I think H0 is non-statistically significantly increasing. And maybe I can see that same pattern in yours. Like there's that 0.03 one that kind of ruins my interpretation, but
this is very wide. Yeah, this is basically okay with everything.
It's another piece of completely not statistically significant evidence that maybe H0 is changing. I mean, H is obviously changing, but that H is changing differently to how the modeling is assuming it's changing.
Right. So I think for FRBs, the more likely explanation is something like this, right? Again, like this is all statistically not significant. Like they are all within their very large errors, they all agree. But if you start seeing a pattern, then what that tells you essentially most likely is that you assumed a different host DM.
Okay, so the host halos are slightly different at different redshifts.
Yeah. So this is essentially how this limit works, right? Like this, the joint fit is essentially trying to get all of the FRBs to be lined up. So the mean host dispersion measure is evolving with redshift. No, but you're right. Like with larger samples, we absolutely have to also be careful about evolution in the galaxies themselves. Yeah.
Oh, I mean, you were saying no. I was trying to interpret deviations from latency. Yeah.
Or something crazy is happening, right? Like
what's coming next? What should we be watching out for?
So with FRBs, it's really more data. It will be very exciting to see what we can do with the next data releases from the dedicated FRB surveys. There are some other things we think about, like more forecasts, like what you can do with FRBs for cosmology. But it basically boils down to like what I briefly talked about, that you have to think about something that you can see on either on very large scales or where it's actually interesting that you're looking at a transient. So there are also papers where you can look at things like the photon mass. Because if the photon is massive, then there's a natural dispersion of the photons as they travel. So there's a frequency-dependent dispersion of photons just in empty space. And that would look like a dispersion to first order, basically. And you can look for these effects. So there's a lot of non-standard stuff, like extensions that you can actually check with these pulses.
That might already have constraints from the closeness to lambda CDM that you're already seeing. I mean, the fact that you've got 62 and Shoes gets 74 or something is, you could have got 3000 if there was a huge photon mass or something. So
exactly, yeah. There are already published limits on the photon mass from FRBs.
And I guess you indicated there's a new paper coming out soonish. I mean, that you've even shared results with us. Thank you for that. So I guess keep an eye out for that.
Will always be more FRB papers now.
Awesome. Other than that, I am changing the final question I'm asking. So this is the first person to have the new question. What work being done in cosmology at the moment do you think is particularly underappreciated by the community?
I think sometimes in cosmology we are now a bit too much in this survey mindset, maybe. I think often, I don't know, with these tensions, we have to look what's actually going on, and this is definitely a problem. But I mean, lots of people are doing that, Hubble tension or sigma 8. A lot of people are working on that. I think there are lots of open questions in basic structure formation that a lot of people are not thinking about that much anymore. I don't know, we can simulate a lot these days, but do we really understand why halos are stable for so long? I don't think so.
Why you have the NFW profile?
Yeah, where the NFW profile comes from, right? Halos look very similar over so many orders of magnitude. And I'm not sure, we see it in simulations, but do we really understand it? I'm not sure. So there should be some, since we see a simple result, there should be hopefully a simple explanation, and I don't know what it is.
No, that's a cool answer. I like this new question. Awesome. Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified. Click like to help with YouTube algorithms and share the channel with your colleagues. If you have any questions or suggestions, then feel free to leave a comment. I'll make sure that Steffen sees it. I guess maybe you want to check out these other FRB talks, which maybe are appearing on the screen at the moment. There's 2 by Amanda, one for this channel and one for the conference channel. And thanks again, Steffen, for the great talk.
Thanks for having me.